presentation, press the Start Broadcast button on the GoToWebinar control panel to allow all attendees to hear you. This system will notify you once you begin your broadcast. The broadcast is now starting. All attendees are in listen-only mode.
Manufacturing to help you design and produce products a lot faster. My name is Rob Romanowski. I'm the Director of Sales Operations with 3HCI, and our special guest and presenter today is Kevin Billette from Envision TEC. Kevin is a veteran of the 3D printing industry and has a fantastic knowledge of a wide range of 3D printers from other vendors such as Stratasys and 3D Systems from his extensive time working for those companies as well as being in the industry. And he's going to give us some insight to Envision TEC 3D printers, which personally I think are the best 3D printers on the market.
Thanks, Rob. Can you hear me okay? Oh, Rob, can you hear me okay?
Have Kevin start the presentation.
Okay, Rob, can you hear me okay?
Yes, hear you loud and clear.
Okay, terrific. Sorry, just making sure everything's up there. Grab that out of the way.
All right, I see your screen.
Okay, good. All right, for whatever reason, it's locking up here. Well, thanks, Rob. Yeah, again, my name is Kevin Billette. I am with the Northeast Channel Manager for Envision TEC. I did want to, just kind of do a product overview today of our lineup. If you're not familiar with Envision TEC in the past, that's too bad, but I just did want to kind of do an introduction of us as well. So we're a 15-year-old company, actually 16-year-old company now, founded in 2002 by Al Sablani. He holds the original patents for the DLP technology as well as 3SP, which I'll get into a little bit later. We are based out of Dearborn, Michigan, in our North American headquarters, R&D, support, and service, and all our benchmarking. And Gladbach, Germany is also our international headquarters for some R&D production, as well as our bioplotter support and development. We also have locations for manufacturing and a few other technical services in California. Woburn, Mass. is our Veritas location. Montreal, Canada, United Kingdom, and Kiev. Chemistry is in Canada. That's where we mix most of our proprietary materials. And then we have a lot of other, just R&D as well in other areas. We have dominated in the dental, orthodontic, and jewelry market for a very long time. So in some of the MCAD we call or prototyping space, probably been a little bit more in the mix, and depending on, again, your exposure to the 3D print world, perhaps it may not have something that's come up on the radar in the past, but in those three markets we had dominated for a very long time. And so now we've got a lot more options out there for MCAD and other options there. So the manufacturing side, we have our biofabrication, medical devices, aerospace, automotive, education, consumer goods. All those things are options we have there. Okay, there we go. Sorry, I was getting my thing wasn't connecting. Mark, sorry, Rob, you can still see my screen, okay, right?
Yes.
Okay, there we go. So yeah, just a quick timeline on there, 2007 up through roughly current. Again, 2002, Al Sablani had founded the company, started off with a few of our smaller DLP printers and expanded technology from there. And it's been increasing ever since in terms of what technologies we offer, but then also the materials science behind them and what you can do with them. So just to kind of go over, so we have 5 core technologies, and there's a +1 there for 6, and I'll kind of discuss why at the end there. But currently, the 5 core technologies we market are bioprinting, DLP process, 3SP with our desktops, our RAM system, and CDLM, which is also a DLP-like process. But I'll discuss each one of these in depth so you understand a little bit more of each one there. Get some stuff out of the way here. So the other thing is our material selection. I won't go into heavily into depth in materials just because we have 50 plus materials in our library. We've actually cut that down recently to 50 because we had so many, but we have to have a more coherent lineup. But we have materials that focus on all of these types of applicational categories: prototyping, dental, medical, castables, molds, tooling, again, the FDA, dental and jewelry area. So we have materials in a lot of those, and we can, unlike other OEMs, I should say some of the other commercial OEMs, can do some formulation of custom materials if a customer so desires it. We have some guidelines around that, but it is a possibility, which is fairly uncommon unless perhaps you're Fortune 50 type of company and some of those other companies. So what we're best known for is our accuracy, surface finish, and speed. Accuracy means CAD to end part, you are the closest in geometric accuracy. That's not about like just resolution. It's about how accurate is the part to your original CAD file. Surface finish, our DLPs can achieve a near layerless appearance in some cases. And then a speed, we have our DLPs are quite fast, but then we also have our CDLM tech, which I'll cover, that is extremely fast in the market. So just again, a quick go at the basics. I won't read through everything here, but there's a lot about debate about accuracy and resolution. They're not the same thing. The accuracy, again, is about that XYZ accuracy to your original CAD file and how well that resolves. So resolution is obviously more of a surface finish. Can you see the layer lines? Can you see the stair stepping? Can you see that artifact that says it's 3D printed? That's usually a little bit more about the difference between the two of them. So just to kind of cover that quick. And then as far as our technology, all of our technologies now in our projection type, whether it be DLP or CDLM, we have a flat, either glass or rigid bottom build tray, which some of the other cheap manufacturers do not. So that does affect accuracy and overall output. So first off, our DLP printers. So that is digital light processing. Again, commercialized in 2002 by us, and the original patents for the DLP 3D printing process as well. On the right hand there, you kind of see a diagram of the basics, the mechanics of this. We have a build platform that rises out of the printer. It rides on a dual rail axis, so it's very stable and accurate with no movement, because one of the key things is it being extremely still and being just rising out in the Z. That is actually one of the only moving parts in this printer, is just the Z axis rising up. So the DLP has a high definition optical projection that uses the slices. Once the print has been sliced into all those hundreds or thousands of layers, each of those layers is exposed by that projector, and it's then transmitted to a DLP chip that's then projected up through our high-end optics. This leads to a faster print than, say, SLA, a superior finish. The pixels can be cured to a different depth, meaning like for brightness. So if imagine a light being brighter, you're penetrating deeper or less deep into the resin to be able to get that layer thickness. And then we also have some patented software and even electromechanical controls to cause like some grayscaling to help smooth those prints out as well. We have a number of different sizes in the DLPs. So again, this is our core technology, so it's been proven over 15 years. Accurate at the voxel level, which if you know the term voxel, it's kind of like a 3D pixel. Easy to switch materials, which is another thing that in a lot of the commercial printing area gets a little difficult. But this one is kind of a quick, it's a tray of resin, so it's easy to pull one out, put another one back in quite quickly. Material usage is much easier to maintain, and you use more of the material efficiently that way without a lot of waste. And again, advanced firmware and software that is ours that deliver better results. This is just a quick view of kind of how that, this is a smaller printer, one of our smaller desktop printers. You can see just the image of the basement there, that PSA, that rubberized tray, and the printing process occurring where that head is dipping in and pulling back out. On the right hand there, you can see some bite guards that were printed. Has supports holding the parts to the upper tray as it pulls up. So those supports are just removed just after printing. So and just a quick thing about SLA versus, say, DLP. So SLA, that process, if you're familiar enough, is a laser fired at a galvo mirror that draws, I'd say, lithography, and that's where the stereolithography comes from, draws on each part to go, to each part. It's very focal. It goes one part, next part, next part, next part, so on and so forth. So no matter how fast that goes, it's slower because it's hitting each part individually, kind of like the way FDM does, fusion deposition modeling, that hits each one per layer, and that's slow. And it also has to compensate for some, if you're not pointing directly in the center, it focuses off on the side, and it causes the software to actually compensate for some ovaling that the laser has. DLP, however, that's a light projection of that layer, so it's the entire layer is projected at once, one single exposure. And then we also have what's called an ERM enhanced module that helps with that grayscaling I mentioned. You see on the left-hand side there, if you think about traditional computer graphics, you have your shape, and then it's all built of pixels, right? But you have some stair stepping from the pixels. If they do what's called grayscaling, that tends to feather out those pixels in brightness to help smooth off that appearance. This is an image of the device that actually, in our per factory systems, our larger DLP core systems, it's an electromechanical device that actually sits around the base of the lens and does a 1 pixel shift, just almost like a judder that causes that to dither and grayscale to help that. And what that does is it kind of almost artificially improves. Well, actually, no, it's not artificial. It improves the overall layer appearance in the Z and the X and Y. Actually, the one where you see those pixels to smooth off any indication of pixeling from that process. So it's actually a very nice, elegant way to do that. So again,
Kevin, there's other companies that boast having a DLP process, and those 3D printers are, let's say, cheaper in price, and I also think cheaper as far as how they're made. So this, I just wanted to point out that this is what the difference is between what another manufacturer might have with a DLP process as opposed to Envision TEC, which has a true DLP process. And as you see here, filling in these voxels more detailed gives you a more accurate print and more accuracy as opposed to resolution.
Right. Well, this one is not only for accuracy but also resolution, right? Because the accuracy has to do with a lot of things like our optics, for one thing, like us cheaper printers that, like, say, Formlabs and stuff like that. They're actually a laser based, but some of the other ones are optics as well. If they're not using high-end optics, your image that you're producing, whether, I don't care if the slice is a square or a circle or obviously whatever shape that is not going to be as true to the final piece. So I mean, we use high-end optics, and like Zeiss or one of our, I was blanking on one of the other companies we use, but they're high-end optics that are one of the key core features of those printers. Glass, tempered glass bottoms. The basements are a rigid metal, and then our trays are a stretched. The tray that it actually contacts, which has a softer contact one, is a pre-stretched one, to a hard base, it's completely flat. There's a lot of factors there that are just improve the overall experience, the overall output. And so, just all our refractory machines you see on the right there, they are all now LED optic systems in terms of the projector. We used to have a lot of incandescent ones, like traditional, DLP projectors. They've all been switched to LED. The LED gives us far more versatility. They're much brighter. If they need to be, we can get more powerful and efficient projections, and sheerly adds a hell of a lot more life. We're talking almost tenfold and life of those bulbs, because where maybe been a few thousand hours with a incandescent, or now 10,000 plus, on an LED. So that was a drastic improvement over those machines. This is just a quick run over of our refractory lineup. Again, the refractories are those, like, our tried and true core machines. What you might notice is that a lot of the build spaces are relatively, I want to say, small on average compared to maybe some other commercial level desktops. But the key here is that we can do these small to medium-sized parts at extremely high resolution and tight accuracies by keeping it a smaller projection area. If you think about your projector, light goes off in a V-shaped beam, right? It's not a laser, so the larger you try and increase that image, the pixels get bigger and your resolution tends to drop out. So, we keep our systems focused on the best size for, the best accuracy and resolution for that. So these are our larger, standard refractories. We also have our minis, and a lot of these minis tend to be like, again, smaller builds, but we're getting accuracies in the XY from 15 to 100 micron, and then Z steps. Our Z step is also a dynamic. Depending on the material, you could be getting 15 microns up to 150 per build, depending on what you want to do. So that is material dependent. Some materials can only do 25 or 50. Some we can push down to 15 in the Z, and then but the accuracy, we're talking 15 to 150 in the XY. Our desktop machines, so these are obviously just smaller tabletop ones versus our freestanding refractories. Still higher end optics and higher quality hardware overall. Still a dual rail system internally on the Z-axis, but again, these are just a smaller tabletop version. Easy to maintain, affordable to operate, still very effective on material usage, because you're just pouring in a little bit more than what you use for that build, and then you can save some of the material as you go. Clean out the basin, and then you go on to your next one, or you can have a couple trays and just put the next one in and change materials out as you go. The versatility there, is impressive. We have very, very similar material options for our desktop as we do our big refractories, so you're not limited to just the machine because it's a smaller one as well. So there's our Vita, is our larger of the desktop machines. You can see there about 5.5 by 3.1 by roughly 4 inches in build area. Again, still a high resolution, 2000th XY resolution accuracy, and then again a dynamic Z from 25 up to 150 microns per layer. I guess a couple of those materials can be pushed maybe a little bit lower than 25, but again, these are still high-res machines. And this is something where it's a higher-end machine, a commercial level, versus, say, Formlabs or some of these other small resin-type ones where your XY accuracies are probably more like 140, So that's where you start to see some of the gains outside of the hardware. And then our micros, which are, again, smaller, more popular. Again, dental, jewelry have been more popular there. But if you need to do small, high accuracy, really high res parts with, say small fluid channels or, details that another machine just cannot pick up, this is where you're going to see a real benefit. These micros, again, you're talking maybe like 4 inches in the Z, but then, closer to 2 by 2 or 4 by 3, smaller builds. But again, you can see the accuracies accordingly on the side there. So that's our DLP, and then so our other technology, which most people are not as familiar with, is our 3SP technology. So that's scan, spin, and selectively photo cure. So these are our larger bed systems. So we're talking, 7 to 8 inches up to 18 inches cubed in our largest machine. So this is a similar to an SLA in that it's a laser-based vat system, but it uses a completely different methodology that actually increases throughput, sometimes 5x, depending on the number of parts and so on. Instead of using those galvo mirrors, it's reflected off of a drum, laser mirrored drum that's 20,000 RPM spinning as that beam hits it, and then it's going through 2 lenses as it goes. Oops, I'm sure. So this is a diagram of that, and so the machine, again, low amount of moving parts. This gantry you see just lifts up and hinges down over top of the vat. The gantry system is really much all of the moving parts in there, aside from the table. And you see on the left-hand side, the mirror. You have your octagonal drum mirror, the 2 lenses, and the UV laser fire, and the optical sensor that's firing to scan across the bed. So this system, if any of you are familiar with, say, jetting technologies where you have a head sweeping across the bed, it's almost like having the benefit of speed and hitting the entire bed per pass versus SLA being, again, very focal on each part. So even though the speed of, say, printing one small part in the center of that machine versus SLA may be close, we're probably still going to be faster. If we had to do 20 parts on the same table, we're going to be way faster because we're hitting all of those parts every pass as we go. So we're getting a lot faster, a lot more throughput. And speed and throughput, again, are kind of 2 different things. It's a speed of print, but then also how many can you do in that allocated amount of time. We also, there's no, used to be a PSA, what we call a stretched screen, like a thin layer across these types of technologies, and our Ultra. That is no longer there. This is a direct contact to the resin. So we get a super smooth mirror-like finish on the up-facing side. So you get a beautiful, any flat surfaces, anything like that, they are shiny right out of the printer. Really nice finish right out of the machine. Launched in 2013. They're much more efficient and faster compared to SLAs. 1/5 the operational cost of a lot of the bigger ones, say from 3DS. And then we're constantly making improvements, as we go. We've moved from the PSA system to a blade, as I mentioned before. And then again, big high production dental. Right now, we have a lot of dental labs. They'll just do whole trays full of teeth molds that they're pulling from someone like Smiles Direct or Invisalign, those types of companies. So again, this is a little bit better, more geared for larger pieces, manufacturing usage. We have materials that have borosilicate glass in them for our E-tool. We have investment casting material, and then again some other high performance prototyping resins. So prints up to as large. Our biggest one is 18 inches cubed. Without sacrificing that finish. Low cost multi-cavity diode laser. So we've now improved that laser we've seen no dip in power over months of use. So that's been improved. Self-calibrating, the ability to use multiple materials, and if you want different vat changeouts. So again, and we have resolutions, and our vectors, we're getting between 50 to 100 micron options for your Z, but then we're down to even 25 microns in the XY accuracy and resolution in our, say, vector UHD, which is a newer unit, but for a larger frame machine, that's pretty impressive. You can't get that in SLA. This is just a quick chart, a view of some of our machines, the smaller one being the Vector. Then we have our Extreme. We have an HD version of both of those machines, and then our huge Exceed one that's 18 inches cubed. Again, like those max resolutions are your XY, most of them being 100 in the Z, except for the Vector can do 50, as well as the Vector HD. if you need it to be. This is a view of that new UHD3 SP. We have a new control board, new lasers, and that picture in the lower right there, that pen tip there. We have this tester block we did, and you can get text. I would say that's probably down to about 8-point to 6-point text font size. Well, and then we can also get like textures and stuff that you probably would never see on an SLA. We have some white papers on this one. On the right-hand side, we have our white paper you can download from our site. Has a lot more info on it. That right there, you can see an image of our E-tool for an injection mold, 3D printed injection mold that we can do in that material. CDLM, this is one of our interesting ones. So this is the technology that we've had since 2006. The patents were filed, but this technology you may recognize it from carbon, because they actually kind of took this technology and ran with it after some of our original patents have come through. But they're obviously still leasing their machines. You can buy ours in this Vita CDLM or Vita HD. So it is the fastest technology offered. This is continuous Z-axis, meaning that it's constantly moving up as opposed to dropping down, up and down, just like our DLPs tend to recoat those parts. And then we also have a patented domeless technology, and what I mean by that is that the base at which, I'm going to go forward one slide here. This, you can see a common continuous printers, this is more referring to the competitor technology, is that CDLM uses an oxygen interface layer that inhibits curing in that space in between, but it's allowed to happen just above it. And this allows for an extremely fast print. We're talking like 3 inches per hour plus on a lower resolution. But what they have to do is they have to actually compensate or lose some accuracy, because that permeable layer they use is flexible. So you get like a 0.4, 0.5 millimeter bubble or dome that's created by that pressure from the oxygen being piped in. But we have a rigid base, so there is no deflection of that base to compensate for. This allows for faster, more accurate printing in our technology. And this technology is probably going to move slowly into our bigger machines as well as we go. So again, the key benefits of this one is just speed. It is an isotropic part, meaning that X, Y, Z, strengths are all the same versus say FDM that has like pure strength, layering and stuff that may be not wanted. And then again, we filed this patent. We've had this technology in development for quite a long time. So we are, I would say, experts in this field to do these extremely fast ones. It's been the most popular in jewelry and dental, because we have these jewelers whipping out just trays full of rings in 2 hours, and then they're right to casting them. So that's why it's been such a huge boom in that area. So you can see our micro and our Vita HD CDLMs. Again, small build spaces. The Vita is probably the best of the bunch in terms of size. You're not sacrificing a heck of a lot of resolution in terms of XY accuracy and resolution. But if you want handheld size prints really fast, those Vita and Vita HD ones are terrific options there. And we have an ever-growing list of materials for this one. High wax content ones for casting, as well as just prototyping materials, so you can get your models out couple builds a day. That's the gain right there. So our 3D bioplotter is one other piece of technology. This is obviously might seem more limited to say that biospace, that we've had a lot of other schools and institutions use it for other things, because it is an open source printing machine, though it is a very, it's almost like a piece of lab equipment as much as it is a 3D printer. So this one's been around for almost 18 years, and it is probably like the household name in the bio industry. Most people know the bioplotter just by name, and sometimes it just kind of sells itself that way. But it comes in 3 different sizes. We have 200 or 200 now 30-ish published papers, and published papers is a commodity in the kind of bio and pharmaceutical industry for all those use cases being tested. Once those papers have been published, it gives them precedent to work from. The next competitor in this area, you're lucky to get 20. So we're talking 10x the amount of published papers out there. Easy to use, for most entry, even to up to commercial level. Again, it has multiple features like UV head, heated and cooled platforms, heated and cooled heads. Its main purpose, is for regenerative medicine for the most part. Again, the fabrication of bioresorbable scaffolds. So if you guys have ever heard of, I'm printing organs or growing organs, for the most part, it's building a lattice in which to have those cells grow onto. So like think of a walled organ or a liver or something like that. They can make a scaffold, seed that scaffold with the proper cells, and then it grows from there in a petri dish or otherwise. And then some of these scaffolds are, made out of a material that then can dissolve in the body, to effectively allow that bone or tissue to heal. In the end, it's at the patient's own tissue, their own body, because that's the end-all be-all instead of something artificial. So bone regeneration, cartilage, soft tissue, drug release, organ printing, those are its main uses. It is like an FDM printer, but it is a pneumatic system, meaning that it's syringe-based with air pressure, pressing that syringe down to extrude the material. That allows for sterile air, sterile syringe to be able to put material down, especially if there's live cells. And that obviously is where, if you're printing into, say, a gel or into a petri dish, you're not worrying about a filament or something coming through that has could be in contact with something, and you have no control over it. This is just a quick video of it printing at one of our trade shows recently. This is our developer series, but you can see like the polypropylene Nordson tip extruding a silicone. Extremely fine movement, quiet, as you can kind of hear, very exacting, and that's just tooling silicone. We actually have a medical grade silicone as well. And so what that does, you can print into wells, fixture plates, all that stuff. The software, you can see an example of patterns. This is actually just a square STL, so square shape, but the software can actually do these ornate patterns. And the reason for these is to allow for nutrients and cellular matter to infiltrate into those spaces the way you want them to, so then they can then grow properly, vascularize. This is a whole other kind of array of science here, but those are all very interchangeable manually, and it's an interesting application. These are like saying an outer shape of like a jawbone there. You see a nose printed out into silicone. But again, these are scaffolds to grow the real thing. It's giving them a shape to grow into, right? So uses raw materials, pellets, powders, etc. It is an open source machine, so it's meant to be using your own materials. Medical grade stuff's available, and then we have a cabinet if you need it, sterilizable cartridges. Again, you're not locked to anything. We have materials, but you're not locked to it. These are the array.
It also prints in metal.
Well, you can do, if you have like a metal paste, you could do titanium or stainless steel or something like that. That's, as long as it's mixed into say a paste, and you can get it the right viscosity to extrude out of the machine, you can then it can stand up on under its own viscosity, whether it be cured or whatever. You can then sinter that out, put it in the sintering oven or evaporation. So we have folks doing titanium or graphene or possibly small steel parts. You just be compensating perhaps for the shrinkage of those pieces. So
yeah, we're in the middle of a benchmark for a customer with one of these, and ideally what they want to do is print this metal material that's a conductor onto these transformers, which are about maybe 1 inch or 2 inches in diameter, so that would be the conductor. And the first step was just completed on the bioplotter, which means that it will print that metal material that they need. So the next step is and it should be able to do this, be able to print it onto the transformer itself. So that's kind of an interesting application that came up for manufacturing more so than medical with the bioplotter. So
Right.
if anybody out there is thinking outside the box and has an application of something similar where that could work, let us know.
Mm-hmm. Right. So, yeah, this is a view of our 3 series: a starter series, developer, and manufacturer. Obviously, the manufacturer is one of those 5 parking spots, sterile and particle filter, all the bells and whistles, camera that can record every layer. So interesting piece of technology. 1 micron accuracy movements in the X, Y, and Z. It is a magnetic drive. It's no pulleys or screws. This is all a magnetic drive. You can kind of see just the options there. The manufacturer has just about everything. Developers kind of that mid-range, good model for most people. The starters kind of there just to kind of compete with some of the entry-level things coming up there with fixed heads and just be able to have a nice pneumatic system. Again, we have all those papers. We have actually all these papers, research papers, on our website. You can go to the 3D BioPlatter site and then 3D BioPlatter research papers, and then you can sort by year, author, keyword, and find something if this is your kettle of fish, so to speak. Veridis, one of the other awesome ones in departure from the resins. So this is our sand printer for sand casting. So it is Veridis out of our Woburn office. This was a small firm that was an acquisition by us a number of years ago, and so their focus is this robotic binder jet system for creating sand casts. So RAM stands for the Robotic Additive Manufacturing. We were the first to release any robotic system out there. This one is, again, for building sand molds, cores, patterns very quickly, very efficiently, and probably with geometry you could never get with traditional machining of patterns. This is just a diagram of the system, robotic head. This is an ABB arm, so the ABB robotic arm that's made by ABB, so it's a very proven, reliable platform. You have the sand delivery system, which is just purely just the sand hopper that goes and retrieves sand, the fluids panel and control, and then robotic, and then we have just post-computer and just some of the build table that may be optional for an automated one versus a static one. This is just a diagram of this. The print head is where most of the science and application is. The side view, you can see there's a trough full of sand, has a spinning screw that helps just drop that sand in front of the spreader. Spreader spreads it flat, comes behind with an array of inkjet heads. So it's dropping the sand, spreading it, and then printing a binder, which is a Furon binder, on there to get the sand to stick together. A sand mold is made up of this sand, just dry sand, with the modified binder jetted into it, and the sand itself has a dry catalyst mixed into it. And that's just via auger. It's not something that it's sprayed into the sand, it's pre-treated, and you can't reuse it. So we have the liquid binder, that's the Puron, the sand, which could be your traditional Oklahomas, Wedgerons. We're working on ceramics right now too. And again, the catalyst is a dry binder, so it's just a dry additive you mix into the sand, either buy from us as a super sack, or you can be shown the proper ratios to mix it yourself. This is a lot of detail of just the sizes available. So we have a 123 and a 224, and then a 236 and a 336, either 12 to 16 print heads, from as small as 1 foot by 2 foot by 3 foot up to 3 foot by 3 foot by 6 foot, depending on the the build out. And that actually is not the end all, because the robotic system allows for growth, and we could we have a system just recently custom made with 24 heads for someone who wanted to do these giant propeller investments that they had to do in multiple pieces before. So that was a terrific example of not being in a box. Like traditional 3D printers, this allows for that kind of growth. Again, that's the ABB IRB 460 model that's hook to. Some people are like, well, isn't a gantry system more accurate? Its positional accuracy is in 0.2 millimeter, and its path accuracy is with about 0.1 millimeter. So it's full Cartesian movement. So that's it's probably as accurate as most gantry, if not, any high-end commercial systems. Silica's, again, foundries are moving away from silica just due to some OSHA requirements. So ceramics are becoming more popular. We can actually use your own mixes. We just have to vet some out and make sure it's going through the head properly. And so that's a huge gain too, because you can use your own sand. You can reuse it because it's just dropping away after it's been brushed out. And then we just use our binder that's viscous enough to go through these inkjet heads. 3,000 system repeatability was in 3.03 overall, and then layers 200 microns up to 500 microns. That's slightly adjustable as well, depending on the sand. Overall accuracy around 9 thou. So for most sand casting, that's perfectly fine. And again, this is for non-ferrous or ferrous sand casting. You can see that, again, just an exhibit of what that looks like in our unit. And I mean, the competition out there, we're talking about X1 or Voxeljet. Voxeljet can't sell into the U.S. right now because of X1's patents. X1, an installation of an X1 in a similar size, you're talking a $1.5 million investment, almost like a metal machine. This one is less than half of that. We're talking like 500 or less. So this gives companies, small foundries, a way to compete in this market, or even companies that have their own foundries, that maybe they're a pipe and valve type of company and they make their own stuff, like someone like Vitalik or something like that, that have their own foundries. This is something else they could look at to keep it in-house. Lastly, this is kind of the plus one, is our SLCOM. So this isn't still in development. We unveiled it a couple of years in 2016. And we've still just been finishing off some development, but we're currently kind of seeking some folks that may be looking into some beta siting of this. But so this is a selective lamination composite object manufacturing, a little bit like LOM. If any of you remember, we're talking 20 plus, almost 30 years ago, the laminated object manufacturing. Similar idea, but this is actually a 4-axis machine. To print in pre-preg composites like fiberglass, Kevlar, carbon fiber, so you get exceptional toughness from the parts, environmental, vibration dampening, all that sort of thing. It's obviously a desktop one, right? So big machine. It uses
I have a big desk.
Yes, a rotational table as well as the three-axis gantry system. You can see, like, by the size of the part compared to the rest of the machine. Uses an ultrasonic cutter to cut away material after it's been laminated together. So pre-pregs obviously already have the resin embedded, and then has to be heated for that resin to to kind of melt before it cures. And then this also has an inkjet head that's essentially a non-stick, almost like a inhibitor for that lamination, so the excess can be cut away by the head after it's been stuck together. High heat, so obviously like pre-preg carbon fiber, high heat, we're talking 100, several hundred degrees, so to make it work. So this is just the preliminary specs of it. So we're talking about 100 micron accuracy XY. The layer thickness is as thick as a single layer of whatever you're using, say be carbon fiber or fiberglass, whatever. Cutting speeds up to like 20 inches per second, and so some of these things may change as we move along here. It's been again, it's in development, but it is a very unique technology to build these laminated pre-pregged parts. So you can imagine in automotive or aerospace, this would be a huge interest. For that. So, sorry for running a tiny bit over here, but do you guys have questions, about anything you saw there? I feel like we do have.
Yeah, if you have any questions, just type those into the questions box, and we'll try to stump Kevin.
I may have one of my other
kind of hard to do.
Matt on the line, but two.
So I'm going to take control real quick here.
And that's my contact on the bottom too, as well as you can reach Rob. But yep, you can always, we work in tandem. So.
Yeah. So what I want to do is just show. What I want to do is give my contact information. If anybody has any questions about what you saw here today, you can contact Kevin. Tell him that you attended the webinar. You can contact us at 3HTI, info@3HTI.com, or you can contact me directly. Or what you can do is, from any emails that you received, whether it was the invitation to join the webinar or your confirmation emails that came from GoToWebinar, if you respond to those, they will come to me, and we can help you out. So if you want to, if you're thinking, hey, I have this, I'm doing something with manufacturing, or I see an opportunity for where a 3D printer and Envision TEC technology could help me out because they really need something with either high resolution, continual accuracy with my prints, or even the wide range of materials that Envision TEC offers with their printers. It's not just, whatchamacallit, cheap ABS plastic. Let us know. We're more than happy to work with you, print a benchmark for you to make sure that we're getting the right materials and the right accuracy for what you need and all that good stuff. So with that, that is going to conclude our webinar for today, Kevin.
Sure. All right.
So Kevin, thanks for being on, and I most importantly want to thank all of our attendees today. And enjoy your weekend, and I will send you a link to this recording so that you can watch it at your leisure in the future. Thanks, everyone.
Thank you, guys. Thanks, Rob.